All right, so welcome everyone to the third lecture in celestial holography by Agata. So Agata, you may start.
Okay, so as I promised, third lecture will be about symmetries on the celestial sphere. Because I mentioned in the very beginning that celestial holography would be nothing without actually correspondence of symmetry, right? It wouldn't be a holography. So today we will investigate the correspondence of symmetries between the asymptotically flat spacetimes and the celestial sphere. One of them we already saw yesterday, right? We saw the correspondence of SL to C and Lorentz. Where is it? Here, right? SL to C and Lorentz generators. We saw how they act on our new celestial basis, conformal primary basis. That conformal primary functions are diagonalizing the boosts, right, in the third direction. And today we will go a little bit further. So we will start with translations. Then, inspired by yesterday's question, I will also spend a little bit of time talking about super translations. We will see how we will see how Poincare symmetry acts on the celestial sphere, right? Because we just saw the Lorentz, we will see translations together, it will be Poincare. And then we will see a little bit more of symmetries of asymptotically flat spacetimes that we haven't talked yet about. And finally, I would say finish the holographic dictionary or symmetry holographic dictionary. All right, so let's start. Lecture 3. Today's green. Lecture 3. Symmetry correspondence. And let's start doing a little table for us to write down the correspondence, to fix it, so we can return to it and keep on filling the lines during our talk today. So we start with symmetries in 4D asymptotically flat spacetimes. And we set correspondence with two-dimensional conformal celestial conformal field theory. Okay, so the first the first line here we already investigated, right? It's the correspondence of Lorentz SO13 symmetry. And Lorentz SO13 symmetry acts on our conformal primary basis as global conformal transformations of a cell to C group. This we already saw. Great. Now let's continue with translations. Let's start a new page. So, translation symmetry. We will just nothing difficult. We will just act with the translation generators on our conformal primary wave functions and see what happens. So we start with our conformal primary wave function. And we, depending on x and z, and we act with the generator of translations. So written in momentum basis, this is the derivative with respect to coordinate, right? So we expand we will, a little note here that today we will talk about massless conformal primary wave functions because it's easier, because for massive case, the expressions are bigger, and I think for intuition of the symmetry of action of symmetries, it's enough to see the massless case. So massive case, if you want, you can do it as an exercise at home. But for the welcoming introductory course, I would say that we will restrict ourselves to massless case. Okay. So the massless conformal primary wave function is given, as we remember, right? Was given by the integral transform called Mellin transform, right here. And d omega times omega in the power delta minus 1. And then we have just our normal plane wave function, omega q of x times x, right? So now what we do is we act with the generator. The only place where it could act is the plane wave. This is exactly what happens. And acting on the plane wave, we obtain the factor of I omega q acting on the exponent, right? So here we have minus I from 0 to infinity, d omega delta minus 1, and then again I omega q mu acting on our wave, plane wave, omega q x. All right. Now the i's given 1 omega, we can put it inside of the power of omega. And q mu doesn't depend on omega at all, right? As we remember, when there is a hat, it's something that doesn't have dependence on mass, on energies, right? It's just the direction. So basically, q just depends on the stereographic coordinates. It points the direction of the vector. So we can write it down in front of the integral, sorry. And what we get is omega in the power of delta, then the plane wave. And now to see exactly what we obtained, we just can do a little trick, right? +1 minus 1, which means that this thing here is nothing else but a conformal primary wave function shifted by in the weight with the weight shifted by 1, right? So it's just phi with the weight delta plus 1 of the same x and the same z, right? So what we obtained is that our momentum, our translations, generator of translations, acting on a conformal primary wave function with weight delta, it shifts our weights and also multiplies it by the vector of direction of the particle, right? So interesting story, right? We obtained that even though Lorentz boosts they diagonalize, they act trivially, right, on our primary wave functions, but translational generators they act as weight shifting operators, and this is something that we will put in our dictionary. So global translations, right? Translations. Mu is weight shifting generators in our celestial basis. So it takes delta and makes it delta plus 1. And it's also important here to write down the translational generator in form of in a celestial basis, right? So it will not depend on x, will not depend on any bulk variable. So we can write it as following. So acting on a particle, for example, we consider action of p mu on a particle k, because we will now write down the expression for the full amplitude, and amplitude has a lot of particles, so let us already introduce the notation. We write it down as follows. Here again, we have the epsilon, which represents the in or out plus or minus or plus, whatever you feel like. But still, since I fixed it already in the last lecture that in is going to be plus, out going to be minus, then let me stick to it till the end. So then we have this vector here, right? No, yeah, mu below. And depending only on zk and zk bar. And the weight shifting generator can be written in an exponential form. This is just if we expand in the Taylor series, you will see that it will give us the weight shifting generator. I will not do it. It's some standard algebra tricks. So great. Now we have it in the form of our celestial space. So now it acts only on the variables of our conformal primary wave functions. And we can proceed to acting with it on a full celestial amplitude, right? One of the amplitudes that we wrote yesterday. Yeah, by the way, I wanted to, where is it? This is our, this is our celestial amplitude. I wanted also to specify that our celestial amplitude can be written in the form of conformal correlation function, right? Of some general form of operators, of conformal primary operators with some dimensions delta depending only on the celestial coordinates, celestial sphere coordinate, right? So here it will be z1 bar, and etc., or delta n, z n, zn, zn bar. It's just for notation, so if you will find it in the literature, it means we just denoted the celestial amplitude. This is it's in the basis directly of conformal field theory. I see the question. The index mu of a hat Q hat has to be covariant. I mean, it can be covariant, it can be contravariant, depending. You can just put it down, up and down using the Minkowski metric, right? So we can just juggle with it. Whenever we need up index, we can write ups index. When we need the index below, we write between the index below, knowing that the metric let us transition between these two things. But yeah, if I somewhere write in the wrong, yeah, here, for example, I write. I see. Okay, I see what the question was. Yeah. I might be sometimes a little bit confusing the indices. Thank you for noticing. Okay, so yeah, that was a little remark on the celestial amplitude that we can just write it down as the correlation function of some primary fields. Okay, great. Now let us finally act with one of the translational generators on celestial amplitude. So acting with it on a celestial amplitude, we get pk on the amplitude depending on some weights, delta 1, delta 2, delta n. What we will get is that it will bring us that factor q k, right? And shifted in one of the weights amplitude. So delta 1, delta 2, delta k plus 1, delta k plus 1. And yeah, delta n again. So our amplitude will be shifted, one of the weights in the amplitude will be shifted. So when we act by the whole set of, let's denote it, beautiful P, that is just the action of the sum of all the translations of all particles, right? The amplitude, the total translation operator. The amplitude in the momentum space is invariant under translations, right? So when we will act with it on the celestial amplitude, it also should be invariant under the translations. So when we act with p mu on our celestial amplitude, yeah, let me write it in this A. This is A is beautiful. Should give 0, which means that when we act in particular on every with every with every particle translational generator, it's like P1 plus P2 plus P3 plus Pn, right? So when we act on the amplitude, first will act on the amplitude. It will shift the weight, the first weight. Second will act on the amplitude, will shift the second weight. The end generator will shift the weight n, right? So we can write down as the following constraint, which is the analog of momentum conservation in our celestial sphere. It's delta 1 plus 1, delta 2, delta n plus a n of delta 1 not shifted already. Then now delta 2 is shifted. Delta n is not shifted, etc., 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 plus a n of delta 1 not shifted, delta 2 not shifted, and delta n shifted. And it all should be 0, right? So this is our basically momentum conservation on celestial sphere. Momentum conservation on celestial sphere. Right, so this is the following relation for the amplitude. Okay, a question, a silly question. Is the amplitude the function whose absolute square gives us the probability of a state transition alpha to beta? What is alpha? Alpha, I mean, yeah, it's just the normal correlation function.
I think the question is whether or not the amplitudes that you're computing have the same interpretation as in standard quantum mechanics as being from giving you some probability density of some state evolving to another state. Yes.
I mean, yeah, it just the states, they are not that you can't like touch these states because they're just like some state with the weight delta, another state with the weight delta bar, and they are defined on the celestial sphere. But yeah, basically that's it. Should be. Okay. So yeah, we continued our dictionary, right? With translations. Now all the global symmetry of our spacetime are satisfied. We found what the symmetry does for Lorentz and transformations and translations. Now an interesting question again that I wasn't going to consider it, but yesterday there was a question about super translations, and I think it's nice and short to write it down, so why not? We can talk a little bit about super translations. So super translations, as we remember, since our space is not just Minkowski, right? It's asymptotically flat spacetime, which, as we remember, has this super translational symmetry. So super translations were generated by the following vector field minus, yeah, I think, no, not just f, which is the function on the sphere, times du. If we now go from, and we want to see how this generator acts on our conformal primary basis. right? So if we to do it easier to go from coordinates u are vector z to the normal coordinates tr vector z, and then it just becomes the derivative with respect to t, right? And we act again with this thing on the wave function. And what we get again, right, we get the following action. It's the Mellin transform, and we act with the, yeah, let me space a little bit. We act with the generator on the Mellin transform, d omega, omega delta minus 1. And then we have our formal primary, plane wave function, which is in the case we can just split it in the following manner: plus e times x, right? So let's see. So here, this derivative over t will only fall on the plane wave again, right? On the plane wave again, and it will give us again the just the energy in front of the exponent. So the only difference that minus I z bar. The only difference is that now it's not just some vector q. Here, this factor can be basically any function on a sphere depending on z bar, right? So we again receive the delta in the power and then the transformation of the plane wave, which we again write down as delta plus 1 minus 1. And we recognize here again the function shifted by function shifted in its weight. Delta plus 1 z, not only z, but also x and z vector. So yeah, again, translations, super translations shift our weights, but also multiplies the wave function on some function f on a sphere, right? So answering yesterday's question, no, they are not the eigenstates. If I remember the question correctly, like if it was eigenfunctions of super translations, no, they are not. They are super translations act as weight shifting generators, operators, sorry. And a nice exercise for you to see that, remember we once specified that some of the special cases of f will restore us our 4 translations, 3 spatial and 1 translation in time, right? When we were talking, I actually can find maybe somewhere. So yeah, somewhere here. Yeah, so remember these are our 4 normal global translations of the spacetime. So for you, exercise using this, I guess I used 1 star and 2 stars. Now we can use the 3 stars. Using this, derive the action of 4 global translations. Derive action and compare of 4 global translations and compare with the result that we just got, this result, right? With the result obtained. Okay, so completing our beautiful table, we get that translations and super translations are both acting as weight shifting generators, operators. Super translations. Okay, so far so good. Great. Now the interesting thing is needed to be discovered. So remember, guys, when we were finding in the very first lecture the Bondi metric, right? That gave us the BMS group, this one. Expansion near null infinity, in this case, future null infinity. We expanded this metric up to, I think, order 1 over R, or maybe, yeah, I think up to order 1 over R in the radius, while taking radius to infinity. And then if we actually we can like continue to any order. Remember me telling this. And we actually can. And if we also let me copy this. If we also introduce the next order, so let me introduce the next order. And this is this will be a paragraph with a mystery yet name. So we introduce the next order. The next order looks as follows. Plus 1 over R for 3. This I already don't remember by heart. dz Bondi mass minus 1 over 4 dz czz bar du dz and the next orders. So everything here, all these notations are not new, right? Bondi mass, shear tensor, except this one. And this thing here is known as angular momentum aspect because it's connected. It can be connected with the total angular momentum in some forms of the metric, angular momentum aspect. So when we introduce this angular momentum, and we also should impose the boundary conditions. Remember, we impose the boundary condition, the matching conditions of the asymptotical data by asymptotical data, I mean, right, the Bondi mass, the shear tensor, and now we introduce the NZ, the angular momentum aspect. So remember, we needed to somehow connect the data on the two celestial spheres. Here and here, to solve scattering problems of particles arriving from the past, doing something together in the present, and going away to the future, we needed to introduce the matching conditions for this asymptotic data. And this is exactly what we are going to do now. So if we also introduce the following matching conditions on NZ of our angular momentum aspect. So matching conditions on NZ. Absolutely analogously, so the NZ on the future past null infinity and the past future null infinity. So you understood, right? They should match. And yeah, again, this, for example, this thing here will be given if we write down the copy of the Bondi metric on the past null infinity, right? So this is on the future null infinity. If we write down the same thing with a little bit different letters on the past null infinity, they should coincide, right? The following component of the metric, they should coincide. Great. So we can also consider then the conservation of a charge, and in this sense, in this case, there will be charges connected to some functions on a sphere, some vector fields on a sphere. I will again, I will not derive this because this asymptotical analysis of the metric, how to carefully derive this, you can, for example, find very nicely done in Strominger's lectures on infrared structure of spacetime, something like this. I think I referred to it several times in my lecture notes, so you probably can find it. I will just give you some knowledge around it, and we will use it in our purposes. So again, we have conserved charges that now are will be expanding our Lorentz group. Okay, so these functions, y, they are functions on a sphere, and the matching condition will imply that the same charge written on the I minus, it will be conserved because of our matching conditions. These functions here, again, it's some vector fields on a sphere. Vector fields, basically also arbitrary vector fields on a sphere. So remember, our translations were generated by functions analogy with super translations. They were given by some functions on a sphere. Here, these new transformations preserving our Yeah, thank you, Rafael. There is the link on the Stromanger's lecture. I'm not encouraging you to do it right now, but like after the lecture, if you want to see how all this uh, structure of space-time at infinities look like, I think it's a very good review. So feel free to look in the link. Okay, so analogy with the super translations that were given by the functions f on a sphere. This is already a vector field on a sphere. And we can also write down the vector field generating these transformations. Vector field generating symmetry transformations. We will denote it as, I don't like the letter zeta, so I will use the xy, okay? So for example, xy on square plus is the following thing, is yz dz plus u over 2 dz uz du plus the conjugated part. So dz bar plus u over 2 dz bar y z bar du. All right. And again, this is some new symmetry that preserves our metric. If we expand the metric to the next order, we will see that this symmetry arises, as well as the super translations that stay still here. And this symmetry will be called super rotations. So these transformations are called super rotations. Why are they called super rotations? Because if we take the vector field yz to 1, z squared, or iz squared, we will receive nothing else but Lorentz transformations. So 3 boosts and 3 rotations. So get 3 Lorentz, 6 Lorentz transformations. Right? Transformations. So these super rotations, this symmetry for our asymptotically flat spacetime, it's basically a generalization of Lorentz group that works on infinity, on null infinity, as well as super translations was generalization of translational symmetry. First of all, let's finally name our paragraph. That is super rotations, super rotation symmetry. And let's look very closely, very carefully at our little dictionary. Look what we got. That Lorentz, just our Lorentz transformations that we just find out is a special case of yz when it's 1 z bar, z squared, and the conjugated thing. This is just this particular case of super rotations. From the other side, we have global conformal symmetry, which is SL2C, which is a particular case of local conformal transformations. So we ask ourselves, maybe maybe this is connected somehow. Maybe our super rotations are just local conformal transformations, or any conformal transformations on the celestial sphere. And the spoiler, the answer is yes, because in general, any function, any vector field on a sphere is should be just each of them should be, for example, the local vector field yz should be just given by any holomorphic function. Is any holomorphic function on a sphere. Function on a sphere. And this condition is solved by taking, this is solved by taking yz, any arbitrary power of z, right? So when we remember our when we remember our generators of local conformal algebra, they were written in the following form. Remember, they were decomposed by modes. And let's now spend a little bit of time seeing clearly how our local conformal symmetry goes into the play. So we need, and again, here I will not spend a lot of time on discussing this, but since our charges, our superrotation charges are conserved, then the S matrix should also be invariant under such a transformation. So if we act with the S matrix, with the charges on the S matrix, we will receive the following relation, right? These charges, I'm acting on the S matrix with these charges. We will receive the following: minus I, some factor, then integral over the sphere, right? Plus minus or minus plus. D3z, our vector field yz. This is some polarization tensor of the graviton, if I'm not wrong, written in the in the celestial coordinates. And this is our this will be the subleading soft factor. I haven't talked in my lectures about the leading and subleading soft factors because it will be like 1 hour talk of what is Weinberg's soft theorem, but if you saw the notes, I introduced there the soft theorems themselves, right? It's just the relation saying that when we have some scattering process of n particles, and when we take one of these particles being soft, so when we take some very low energy graviton or photon or any massless particle leaving the one of the legs of the scattering process, the amplitude factorizes as some factor, some kinematical factor, depending on the on the momenta of the graviton and all the other particles times the actually n plus 1, right? Because there is n legs plus 1 leg. It factorizes on some factor depending on omega and mass momentus of the particles and the moment direction of the graviton itself and the previous unbothered amplitude where there were no soft graviton. I will not, maybe in the last lecture we will talk about it, but for now it's just, I will just say that this relation gives us, we can actually expand this factor in the powers of soft graviton. So the leading factor will be 1 over omega. When omega goes to 0, this explodes, right? It gets very big. Then we have some factor of some factor subleasing term times 0 power of the soft momenta, soft graviton, soft particle, which means low energies, right? And we can continue it very, very, very for a very long time, etc., etc. So here the important part is that there is a direct connotation between these soft theorems and the asymptotically the symmetries of asymptotically flat spacetimes. You can read about it in the notes. I mentioned it, or also in Strominger's lectures, where it derived in details. Here for us, just important that this factor here is connected to this subleading soft theorem. Meanwhile, the leading factor was connected to the translations, super translations. Super translations. But that's not the focus of our lecture. So when we again bring this to the form of, we use the form, we know the form of this subleasing soft factor, okay? And when we substitute it in our derivation, we will get the following expansion for the factor. Here we sum over in and out particles of our process. This is just the fact of how we write down this factor here, this subleasing soft factor. And what we get is the following combination of our generating functions, right? Generating functions of superrotations, the y's. Okay, great. So this is how our S matrix transform under the superrotations transformation, superrotational transformations, right? Look at this term now. Look at this term and remember the word identities for conformal field theory that we were, where is it? Where it was? Here. Not here. Yeah, right here. That we were writing down. So it reminds us very much this thing here. Because so we just recognize in the word identity generated by asymptotical symmetry, we recognize the conformal word identity corresponding to the local conformal transformations. And indeed, if we now, for example, take the function, the generating function to be 1 over z minus zk. And then we also define the stress energy tensor as follows. Z minus w dw squared, dw bar, and w bar, w bar. Then our word identity, this one, this is the word identity for super rotations. It will take the following form. So let's denote it as 4 stars already. The word identity 4 stars will take form of t, t, z bar, o, 1, o, m, equals to sum over particles. And here we have very characteristic for any conformal field theory enjoyers thing. So with a little bit of difference that now we consider the conformal two-dimensional conformal field theory on on a curved spacetime, right? So the asymptotically flat spacetime is slightly curved, which means we will have this term here that we usually don't see when studying 2D CFT, right? So now we write down our word identity in the following form. And this is the up to Christoffel symbol coincides with the word identity for two-dimensional CFT. And there will be reference in my notes that I will send after the lecture that will show that the two-dimensional CFT on curved background, the word identity looks exactly like this. So this is the word identity in 2D CFT on a curved background. So concluding our little dictionary here, right? What we got here is that super rotational symmetry superrotations for shortness correspond to local conformal transformations. And basically, that's the story I wanted to tell today about the correspondence of symmetries in the bound and on the boundary. Now we can, with a full confidence, call this thing holography, right? We just saw the correspondence of the symmetries. Now, yeah, so we spent just 1 hour. We can also look in the thing now, little cute thing characteristical to celestial amplitudes, celestial basis called the shadow transform, which is useful, but our big chapter of correspondence of symmetries is closed now, okay? So now we have some time to look into more specific properties of conformal field theory, of conform celestial safety. So let's continue since we have time, which is great. Okay, before I start, these Christoffel symbols are related to the curved aspects of the bulk? Yes, they are. They are. Again, there will be a link, the reference of on the article about safety in curved spacetimes. I mean, you can also maybe Google it somehow right now, but you can just wait. I will send some links. But yeah, they are related. Okay, so to finish today, we will introduce so-called shadow transform. And we will see how the basis, that there are some relation that makes us able to relate the basis function, the basis wave function inside the celestial CFT that we introduced, that they are not completely independent of each other. So if, let's start with definition again. Let's call for a given two-dimensional conformal primary operator O with some weight. Its shadow or tilde we will denote is non-local because it's in the different place, in the different point. It will be in the different point. Non-local operator defined as follows. So the O tilde of some W is an integral transform delta minus 1 over P. This is some normalization things. D squared omega 1 over minus, oh, not omega, W 2 minus delta or delta W prime. Here also W prime. Yeah, I think That's fine. So this is this integral transform is called shadow transform, and it's important to notice the following property of it that we can actually transform our conformal primary wave function and get wave functions with a different weight. So if you do the transformation of a wave function, the shadow transformation of a wave function, we will get nothing else but the wave function with the weight of 2 minus delta, the same point. So if we do a shadow transform, right, the shadow of wave function with the weight delta, we will get the wave function with the weight 2 minus delta. And now remember the times when we were calculating the massless limit of our conformal primary wave functions. Where it was, yeah, here we were computing the massless limit, and if you read the lectures, we saw exactly how to obtain this limit of the propagator. And now, last time when I was talking about it, we just did the integral transformation with first term in the propagator. Remember, so we substituted this first term inside our massive wave function, and we got a massless limit using the delta function, right? Now, actually, if we take this, expression for just a second, for the propagator, and substitute both of these terms in our integral, right? So if we substitute both of them inside the integral representation of our wave function, so measure, remember, times propagator times our plane wave. So if you substitute now both of them and do the coordinate transform, we will get nothing else but a wave function that we defined plus its shadow. So let's write it a little bit more explicit. So when we take the massless limit, right, we get some, I will not write down the normalization factors. They are something, normalization factor 1, right, which was just our normal Mellon transform in just px plus normalization factor 2. And there, since we don't have the delta function, remember the delta function basically ate 2 of the integrals for free. 2 of the integrals from this measure, the measure is the following: 3 is 3-dimensional measure, and the delta function in the first term just deleted these 2 integrals. In the case of the second term, it will not be disregarded, right? So there will still be this 2-dimensional integral. 2-dimensional integral, we just rewrite it here, right? Just rewrite it. And now, yeah, and now we have the rest is the Mellin transform again, with some different with some different weight. So if we rewrite it now, this second integral here for the shifted dimension delta prime, that is 2 minus delta, you see where it's going, right? Already, the powers are already reminding us the shadow. It will be clear that the second term is just the shadow transform of the first one. Okay, I can just. Yeah. So we just see that this thing here, this will be rewritten as 2 times 2 minus delta prime. This will be omega in the power, it's difficult, delta equals 2 minus delta prime, so it's 2 minus delta prime, right? So it's plus delta prime. Yeah, everything is fine. So it's delta prime minus 1, right? So we see that this is nothing else but this integral here is the wave function with the weight 2 minus delta, right? And this part here realizes the shadow transform of the wave function. So this whole thing here is just the shadow transform of our wave function. So basically, even though I deceived you a little bit when we were first deriving it, right? I didn't write the second term in the mass for the massless wave function. Actually, this term was not linearly independent of the first one. So we indeed can just use the first term, and the second one will be given by this integral transform. So yeah, this is what I wanted to say about shadow transform, that psi and psi2 minus delta are not independent. These basis functions, and are given by these transformations on each other. I think that it's a good point to stop for today. There is also maybe something that I wanted to tell, but it's more like specific knowledge that actually using these constraints arising from Poincare symmetry, we can restrict the form of the 4-point celestial amplitude. I added it in my notes. I think it's a little bit more technical. It's not that difficult to see, but basically what we will obtain is that the there is a special. Remember when we obtained the function? Where was it? 3-point function. Where it was here, right? there is some, there is some constraints arising from Poincare symmetry that act on 3 and 4-point functions that can give us additional constraints on this factor here. And in the case of the 4-point function, it gets a little bit more interesting, but I think it's a good point to stop for today. Thank you for your attention. I think the most important part is this table here of the holographical duality. And yeah, if you have any questions, feel free to ask. I hope you appreciated the beauty because I think right now we are on the peak of celestial holography. So this is the motivation, the full motivation of this celestial holographic correspondence. Thank you for your hearts and for your claps. Your